Good morning, TC Oceanography. It's about 6:30 here. This morning's musical guest is Alkaline with Ocean Wave. I was trying to get an ocean theme for each video. I have no idea. Sounds pretty good though. But anyways, hope you guys are doing good. Okay, I'm not sure. But anyways, welcome to our second presentation for oceanography. This is going to be early Earth and origins of life. And my prop of the day, I have this shark jaw. I'm not sure it'll fit. Right? You can see that. Look at all those rows of teeth. I collected this in the Hawaiian Islands. I was on a shark survey, and one of the sharks that we pulled up was dead. So I was able to harvest the jaw. And if you can look, there's several rows of teeth. We'll talk about sharks a little bit later. But anyways, so hopefully you made it through the first presentation. Hopefully we're doing these face-to-face. But this next one, there's going to be three videos in this series. But this one's about early Earth and origins of life. For us to truly understand the ocean, we need to understand where it came from. I'm not going to spend a whole lot of time on Big Bang and formation of the universe because of time. Like I said, I'm trying to make up for 3 weeks of lost class, so we're going to hit some main points here. But so why do we care, and how old do you think life is? So pause the video for a second, jot down some of your thoughts on why do we care about the early Earth and origins of life, and how old do you think the life is? So go ahead, pause the video, reflect on this. You may never had to, and then feel free to unpause me. So when we talk about geological time scale, we usually look at millions of years, billions of years, those kinds of things. So let me go from... move this. If we start actually on the right side, this is where we are with the Paleocene, right? Tertiary. These are periods and epochs. I'm not going to expect you to memorize these, but if you notice, you have these long periods of time where things may be static, and then you start to see emergence of life, and life did evolve in the sea. And so you move into these different periods, right? You've heard probably some of these, especially if you get up into the Mesozoic, so Triassic, Jurassic, Cretaceous. We may talk about the KT event, the day the Mesozoic died, which was a massive extinction event that moved into the Cenozoic. And then we think here on the left, most of our evidence shows us where life may have began, but we definitely have life. We are all the way up there at the Cenozoic, so we're just this little sliver up here, right? We're just this little sliver. And so how this is going from large to smaller time. So if you look here, here's Cenozoic here, give me a broader definition, but it's just showing you that little sliver of life that we are, and this is the Precambrian. So you may have heard of this before. I wish I would have spent more time on this in biology, but this is just kind of giving you an idea that life is very old. And life evolved in the sea because the seas and the oceans had all of the right ingredients for life to occur, if you want to think of it like as making something. So here's Earth's age and time. There's geologic times, eons, eras, periods, epochs. And again, I'm not going to expect you to memorize these, but I just want you to know that we're going to talk about these, but the ones that I want to kind of focus on are when we talk about, let me move my face. We look down here, Archean, those kind of areas, we see prokaryotes down here, oldest surface rocks, oldest moon rocks, and as we move up, you're going to see more complex organisms in the fossil record. And again, as we're up here to modern humans and earliest humans, Quaternary period, we're currently in the age of the mammals, Cenozoic era, right? And so there were some major extinction events that I think are important. So about 66 million years ago, 208 million years ago, and then 252 million years ago, there were some extinction events. And I'm going to pull this into the screen so you can see. This is from HHMI, but this is, and I may share this with you, this is the make and mass extinctions. And so once extinction events occurred, this is when you see the emergence of new life forms, because in death comes life, if you want to think of it that way. And so if I click on these different letters here, it'll take us, what is the extinction rate? What does it tell us? So here is, different extinction events, which I'll share with you. But a lot of them, you're gonna be looking for evidence of these extinction events in the oceans. And so you can see environmental factors, a decrease in CO2, decrease in carbon, decrease in oxygen, but you had rapid growth of, land plants. And then if we look at the Permian and Triassic, right, environmental factors, covered vast areas of land, huge clouds of sulfur dioxide. About 96% of species, especially amphibians, reptiles, insects, trilobites, sea scorpions, and corals, went extinct during some of these. And then Triassic extinction, right? Again, if you look at a lot of these that go extinct, a lot of them occurred in the ocean. Corals, bivalves, which are things like mollusks. And then if we get here, to this Cretaceous extinction, right? This is the asteroid impact. If you had me for biology, we talked about the KT boundary. 76% of living things went extinct. But again, a lot of these were a lot of land dwelling animals. So like your dinosaurs, pterosaurs, mosasaurs, those things. But anyways, so extinction events are important because when we're studying the oceans, we have to understand where we came from. So let me get this out of the screen. All right. So there again, I just showed that to you. So these are the big 5 mass extinctions. And again, I will share this with you, but you can, and are we currently in a 6th mass extinction? And is that due to climate change and the impact that we are having on the environment? As I'm currently recording this, we're expecting a landfall of a hurricane in Texas. I think their names were Laura and Marco, and I haven't been following it, and I should, but anyways. So archean Earth system, so when you ever see that term GA, that means billion years ago. So archean are the archaea. These are your ancient bacteria. The first forms of life on Earth were prokaryotes, or organisms that lacked a nucleus. And so they think, all this evidence suggests is that the Earth was bombarded, there was bombardment from materials from space. And so the atmosphere, hardly any molecular oxygen, but it appears that about 2 billion years ago, early life was probably anaerobic, which means it did not require oxygen. UV radiation, there was no ozone shield, and so early life was probably underwater because of the fact the water would provide protection against the UV radiation because there was no ozone shield at that time. Carbon dioxide, methane-rich atmosphere. Oh, and the lights went out again. Give me a second. It's a great song, The Night the Lights Went Out in Georgia. The Night the Lights Went Out in 102, and it's actually morning. Anyways, back to what I was saying. And so likely you had warm water conditions, about 80 to 80 degrees to 45, high rate of heat transfer, that probably should be flipped. High heat of transfer from core to surface, thin crust, maybe plate tectonics were starting, and so step towards life. But for life to occur, you had to have a synthesis of biomolecules. Those of you had me for AP Bio, we discussed this. So you have these biomolecules being synthesized, you organize them into a system, becoming more complex. Excuse me, I don't have COVID. All right, got it. I'm COVID negative. Anyways, emergence of self-replicating. So you see RNA world hypothesis, and then eventually you'll see emergence of molecular evolution. So the Miller-Urey experiment, this is probably the most important experiment we talk about in terms of paleobiology and evidence for how life formed. So Miller and Urey, they ran an experiment for 1 week, and basically they set up early Earth's atmosphere. And they were able to create, or they were able to model early Earth's atmosphere and create some of these early molecules that would be important for the formation of living things. So they ran an experiment. They observed about 10% of carbon in organic form and about 2% of carbon amino acids. And so, but too high energy environment, lightning, right? It was not continuous, and the early Earth contained appreciable carbon dioxide. So on the other hand, meteorites do contain appreciable amino acids. And so the idea was they modeled it. All models are wrong, but they pretty much were, they were able to model early Earth's atmosphere. And then a modern day Miller-Urey experiment by Jeff Batt at Scripps Institute, he redid the experiment and found there was 22 amino acids he was able to make. And that was more than Miller and Urey. And he also analyzed the original Miller-Urey vials using techniques. And so what does this tell us? When we talk about origin of life on Earth, hot volcano and cold soup models regarding it. So organic molecules, amino acids, can be synthesized by mineral lattices as templates. And what I mean by mineral lattices is if you look at the sea floor where these hot spots, where this material is pouring out of the between these cracks in the plates or whatnot, they can form these lattices to act as a template. And so here's a schematic evolution of life on Earth. So billions of years ago, here we are at the top. Here's, well, we've got a little sliver. Mesozoic, Paleozoic, Proterozoics. You see eukaryotes starting to appear, Archean and Hayden. So what I want you, I'm not expecting you to memorize these periods of time, but I want you to see that Earth started out very simple, probably in the oceans because it provided protection, and over time, due to natural selection and other evolutionary forces, that's where we're at. And that's why we can say with a lot of proof and a lot of evidence that life evolved in the ocean. There's some other things that are interesting. If we look at strolomites, these are biofilms of cyanobacteria capture and bind sediment. So these strolomites, so biofilm is when bacteria grow in large clumps. Cyanobacteria are these bacteria that could do photosynthesis, and so we have these remnants of these strolomites. So in opinion, true consensus for life needs to be reached only when the bacterial fossils of about 1.9 billion year old gunflint formation. So again, this is just fossil evidence to show you that life is old. So we've got some candidates for early Archean fossils. Again, these are just some images here. And then, again, more evidence for life on Earth. So there's some microfossils. I can show you where they spiked, where you're going to see these spikes in the number of microfossils here during this period of time. So about 1 billion years ago, you can see kind of a spike. Again, strolomite taxa, again, you see where they kind of increase. Evidence there. And so that's it. So what I want you to get from this is that A, the Earth is very old. There's lots and lots of evidence for the age of the Earth. 2, life evolved in the ocean because there was protection because there was no ozone present, right? And so that due to changes in evolutionary forces, that's where we're at. So anyways, hopefully this helped. I'm going to try to put back on this song. Alkaline Ocean Wave, which is the official music video. Dance on. Alright, that was just a quick overview of life on Earth, and I'm signing off from 102. We will see you in another video.